having given the examples of motion control systems using certain hardware, you recall the hardware we have used. We have used a DC motor for the actuator, a DC tacho generator for the speed sensor, a potentiometer for position sensor, and other suitable hardware were used to give you examples of motion control systems. Under motion control systems, we have taken position control systems and speed control systems. The objective for today's lecture is to reintroduce the same concept of position and speed control system, but through different hardware. The merits of the hardware being presented today vis-a-vis the hardware already discussed should be clear from today's lecture. That is, the emphasis is going to be on AC components instead of DC. I am going to have an AC sensor called a synchro. I am going to have an AC motor called an AC servo motor, a two-phase servo motor, and other appropriate devices to constitute an AC motion control system will appear today. An important class and its application also will be highlighted. So, to get going, I will like to first take up the actuator of such a control system, the two-phase servo motor. The two-phase servo motor is an actuator which is going to produce the required torque to actuate the load. So, as is evident from the name, this is going to have a two-phase system. It is a two-phase stator, and let me say that this is one phase and this is the other phase. I will call one of these phases as the control phase. The reason will become clear soon, and this is my reference phase. Fine. Now, on this particular rotor is the load, and whether the load is direct on the rotor or through the gear train, I can model it like this. Now, you know it very well. Let me say that J and B are the parameters of the load. I assume that the rotor produces a torque Tm and Tw is the disturbance torque on the motor, which naturally opposes Tm, okay, as per the schematic diagram. So, in this particular case, now what I do is I put in this particular circuit a phase shifting capacitor. The idea is this, that the two phase supply I should be able to get through a single phase voltage supply available to me. So, if I have a phase shifting capacitor here, the natural consequence will be the phase difference between the two phases here is going to be 90 degrees. So, this reference phase, let me say, has got the voltage supply ER cos omega CT. Omega C, the name, the frequency, as you will see shortly, is a carrier wave frequency. The C is coming because of that reason. It is the carrier wave frequency, and ER stands for the reference voltage. Okay? For reasons to be made clear shortly, I put a modulator here, a modulator, and this is the AC supply here. And what is the input to the modulator? The input to the modulator is the control voltage EC. I need your attention here that the input is control voltage EC taken over here, which is always in a control system a low frequency voltage. Recall the specific objective of EC. What is EC? EC is an error signal. EC stands for an error signal in a feedback control system, and the specific objective of the error of the control system is to nullify this error, to reduce this error to 0. So, typically if a control system is functioning well, this error E is going to be a low frequency signal. It is going to be a small signal, and let me take a typical error signal of this nature. Let us say this is the error in the controlled position and the reference position, or it could be the error in controlled velocity or the reference velocity. So, in this particular case now, if this EC signal is the input to this motor, I will like to modulate the signal. So in this particular case, the modulating frequency is going to be omega c, which is the carrier frequency. So let me take the nature of the signal, let me see what the nature of the signal will be when the signal reaches the control phase. I take this as the carrier frequency for the modulator. Okay. So this is my omega ct, cos omega ct signal. Fine. Let us see what is the nature of the signal. I call that as EM applied to the control phase. This signal will look like, as you know already, a modulated wave of this nature. The envelope of this particular wave, this I need your attention at this particular point. I will be using this concept in the derivation. This is the envelope of this particular wave, which is a low frequency signal EC. Okay? How about this carrier? Now just see that when EC is positive, your attention here, when EC is positive, I take this signal EM to be in phase with the carrier, and therefore when the maxima of this comes, the maximum of this will also come. My diagram may not be clear, very clear, because it is a rough diagram coming to you, but you see that the maximum and the maxima of this coincide, so that the phase of EM, that is EM, the modulated signal, is in phase with the carrier signal. Now when the sign of EC changes, in that particular case the phase reversal will take place. So it means in this part of the curve, EM should be anti-phase to cos omega ct. Let me show it this way. This is the maxima, so let me show it just opposite. This is the minima, so here is the maxima, and so on. So now again the phase reversal is taking place at this particular point. So in this case again EC becomes positive, and hence EM will be in phase with EC. So making EM will be in phase with EC is your responsibility to draw a suitable curve. What I want to say is this, that at this particular point where the EC changes its sign, the phase reversal of the EM signal occurs, and it is because of this phase reversal, the reversal in the magnetic flux takes place, and hence the direction of the motor reverses. So this is a bidirectional control system, bidirectional control motor, wherein for EC positive, okay, the motor is moving in one direction, and for EC negative, equivalent effect being in the phase reversal of EM, the rotation of the motor will be in the reverse direction. So that way EM is a carrier modulated wave at frequency omega c, and the reference voltage is at frequency omega c. These two voltages given to these two phases will produce a torque on the motor, and the torque naturally is going to be a function of the magnitude of the voltage EC, ER being fixed. It is going to be a function of the magnitude of the voltage EC, and its direction is going to be a function of the polarity of EC. This should be very clear. Now let me see how this motor behaves. If I make a torque speed characteristic curve over here, this is speed on this axis and here is torque on this axis, and if an experiment is conducted, the results will be of this nature. You will please note that I am very clearly showing here that the curves are non-linear. So it means an AC motor is effectively a non-linear device. There is a non-linear relationship between torque and speed. Recall the case of DC motor. In the case of DC motor, let me just show it in a separate window arrangement. In the case of DC motor, it is the speed, it is the torque. The torque speed characteristics are almost linear. So it means a DC motor is a linear device, while an AC motor is a non-linear device. A positive point for selection of the DC actuators, because your mathematical model will be linear in nature. This point should be noted over here, that the linear characteristics of a DC motor is a positive attribute, because the mathematical model will be linear over a wider range of operation, while in this particular case the mathematical model may turn out to be non-linear if the range of operation becomes too wide. Okay? However, the AC motors still have got certain advantages, and these advantages will become clear. So in this particular case, the AC motor characteristics, if I linearize, a linear curve appears like this. But what should be the region of validity of this? Fortunately, AC motors in position control systems are quite useful. The reason being, your normal operating point is this. Please see, in a position control system, what is the steady state position? The steady state position means speed is equal to 0. That is, the actual position of the load is equal to the commanded position and the motor is not moving. And under equilibrium state, under the steady state, the motor is at standstill, and therefore speed is equal to 0 is the equilibrium point of position control systems. And around this particular point, you see, even from the nonlinear characteristics, you have more or less linear region, and therefore for position control systems, AC motors give reasonably accurate linear model. And therefore, for the purpose of modeling, I can forget about the nonlinearity. I can assume as if the characteristics are given by these linear curves. This point may please be noted. There is a strong assumption involved in it. You see, when I am writing a linear model, the linear model is not valid for the entire region of operation. The linear model is valid under the assumption that this is my operating point, which is speed equal to 0, and around this operating point the curves are linear. And therefore, I am going to use AC motor as a linear device throughout my discussion under the assumption of this being the equilibrium point, and which is 100% true as far as position control systems are concerned. Okay? So if that is the case, what is the torque? Let me write the torque equation. The torque equation becomes simple. K1 Tm should depend upon which factors, please? It should depend upon speed, obviously. As the speed increases, the torque decreases, and therefore the slope here is going to be the governing factor between the relationship between torque and speed. So this is slope K2. What is the other factor? The other factor is going to be control voltage. Recall, EC is the input to the control phase. If EC is equal to ER, then let me assume that this is the curve. Let me call this as EC1. This is EC2. This is EC3. Please see that EC1 is greater than EC2 is greater than EC3. So it means the torque is going to be a function of the control voltage and the speed. When the control voltage increases, the torque increases. When the speed increases, the torque decreases, and hence as a perturbation model, mind the statement, a perturbation model means that in this region around the equilibrium point, I can write the equation as K1 EC minus K2 theta dot, where theta dot is the position. Okay? K1 EC, K2 is corresponding to the control voltage, and K2 theta dot corresponds to the speed torque relationship. Once these curves are experimentally determined and given to you, the mathematical model can easily follow from these experimental curves, because K2 you can determine from here. How about K1, please? Tell me, how will you get the value of K1? Very easily, from this data itself you can make a different plot. That is, I can make a plot between control phase voltage EC on this axis and torque on this axis. Let us say this is the curve for omega equal to 0. And for different values of omega you can take, for omega is equal to omega 1, for example. So in that particular case, what is K1? K1 is going to be the slope of this particular curve. They will be more or less linear in a linear model, but however this is an assumption that the linearity assumption we are taking up for a nonlinear device, which we know is true for a restricted range of operation. So if I plot control phase voltage versus torque, taking speed constant, I get a line whose slope gives me the value of K1. K2 is directly available to me, and therefore this becomes the equation for the torque developed in the case of AC motor. Okay? And
error signal does not have a constant value. So what what do you take as the value of EC?
I have never said that error signal is a constant. This is actually a torque speed characteristics you have experimentally determined for a motor. These are not the error voltages in a typical feedback control application. When you want to determine the mathematical model of a system, you will conduct the experiments. So what you will do is, you first give EC1 is equal to ER, a constant voltage to the modulator, determine the torque speed characteristics for this. Change the voltage. For a particular curve, you are keeping this voltage constant. So when you are experimentally determining the torque speed characteristics, then this is an applied voltage to the control phase and need not be related to the error voltage, because then you are getting these curves for different voltages. What is the effect of varying voltage is coming through this particular equation. Is it all right, please? These are not the curves for a feedback control system. These are the curves you have obtained in the lab by experimentation, and therefore keeping a voltage constant for a particular experiment is in your hand. Is it okay? Fine then. Going to this equation, Tm equal to K1 EC minus K2 theta dot. What is the load on the motor? The load on the motor is equal to J theta double dot plus B theta dot plus, let me write, TW. This becomes the mathematical model of the motor under consideration. Okay? See this point. This can be written in the form K1 EC equal to J theta double dot plus B plus K2 theta dot plus TW. Okay, I can now write EC is my input, EC is equal to, or well, probably we can directly take up the block diagram form, that will be better. EC is the input, you will help me here. What is the other signal coming? Between EC and theta, if you are interested, this is given by this equation, and TW is the disturbance torque on the system. So I can take over here a constant K1 to generate the signal K1 EC. Okay, now I can put a summing block over here and take a signal TW here. This is the net torque now which is driving the inertial load, and now I can put an inertial load over here. What is this value? 1 over Js plus B plus K2. This is your omega here. So if I am interested in a transfer function between omega and EC, the block diagram is complete. But if you want to bring the position into picture, put an integrator, this is a position here. This becomes the block diagram of the total system. You will please note. In this particular case, if I am interested in the transfer function between omega and EC, or between theta and EC, the transfer function will look like, help me please, between omega and EC. What is the nature of the transfer function? It is K1 over Js plus B plus K2. Okay, I hope this is all right. K1 over Js plus B plus K2. This is the transfer function. Now can you tell me what is the effect of K2? Please see, K2 is adding to the damping of the system, the mechanical damping of the system. So it means it is behaving, as far as damping is concerned, the way the DC armature controlled motor behaved. Please see, K2, that is the AC motor, is adding to the damping of the system, and the time constant of the system becomes J divided by B plus K2, where K2 is a parameter of the system. Okay? So I take this opportunity to explain one point to you. A typical induction motor, a two-phase induction motor, as you know, has got this characteristics. My question to you is that, can I use this two-phase induction motor for servo applications? I put my question again, and really I am expecting an answer from you. And to give you the hint, I will tell you that concentrate on this equation, that the relationship between omega and EC is given by K1 over Js plus B plus K2, where K2 adds to the damping. Okay? Now if I take this characteristics, this which is the characteristics of an induction motor, that is if I use induction motor for servo application, do you think there will be any problem or the system will behave appropriately as per your expectations? Yes, any answer please?
B plus K2 may be less than 0. In that case, it will.
That's right. The answer is correct please. In this particular case, you will please note that for an induction motor you are working at this particular speed, but for a servo application you are working in this region. So if the slope becomes negative, in that particular case what will happen? If K2 becomes negative, this amounts to negative damping, and negative damping depends upon what is its magnitude in relation to B, can even lead to instability, or the hunting naturally will come. Too much of oscillations naturally will come, but it can even lead to instability because of this damping, because K2 has a negative sign. Now it depends what is the net damping, that will depend upon the magnitude of B. The magnitude, that is the B value, has to be extremely high to take care of this negative damping effect, and it is because of this reason that this characteristics is never allowed in servo applications, and hence an ordinary induction motor cannot be used for servo applications. By servo applications I mean position or speed control systems. What you need is, you need this characteristics. You will recall this is the characteristics we had drawn, and in this characteristics the slope is always positive, it is never allowed to be negative. And how do you get these characteristics? These characteristics you directly get from the induction motor only by using high rotor resistance. So you see that a servo motor is nothing but an induction motor of high rotor resistance, so that the characteristics of a servo motor always has a positive slope. So you are paying a heavy price as far as efficiency is concerned. High rotor resistance means the net efficiency of the system is going to be low, the net efficiency of the motor is going to be low, but naturally we cannot help it, because our specific application is a servo application wherein the negative slope is not allowed. So in this case this point has to be kept in mind, that in induction motor, if you are using for servo application, redesign it or take care of this point, that it always has a positive slope. Okay. So with this now I can go back to the motor model. The motor model looks like this: omega divided by EC is equal to Km, the motor gain, divided by tau ms plus 1, where tau m is the mechanical time constant of the motor. Okay. This is a first order system between speed and the control voltage. Now if you are interested in an equation between theta and the control voltage, it is going to be a second order system. It is Km divided by S into tau ms plus 1. Okay. This is the mathematical model, which as you know is identical to an armature controlled DC motor, a second order model. At this particular point will need your attention on this system block diagram once again. You will please note that I have taken a transfer function between EC, the control voltage applied over here, and theta m or theta, which is the position of the motor shaft. What is this EC? EC is the control phase voltage, which is a low frequency signal. Consider a situation, you see, consider a situation in a control system that the control phase voltage is directly a high frequency signal, a modulated signal. Your attention here please. It means the input to the control phase is Em and the output is theta, and you are interested in a transfer function between Em and theta. So now input output pair of the system could be taken as this way. What is input? Input is equal to Em, which is of this nature, and what is output? Output is theta, the position. Yes please.
So why are we defining EM versus theta? Why not EC by theta? Theta by EC as we were doing.
This is what I was going to say. I thought in that particular case I could have delayed this discussion, but okay, let me re-emphasize this point. In a typical control system application, this is fine as far as the motor model is concerned. In a typical control system application, the input to this particular motor is the signal which is going to the control phase. Okay? Now I said that, as I will illustrate it through applications, in some systems there are devices which are connected onto the left hand side of the motor, that is the devices whose output is given to the motor. Those devices may be directly producing a modulated signal. See this point please. I think I have confused you, so I will like to make this point further clear by taking a feedback control system. I take this as feedback control system, plus, minus, an amplifier or any other device, and this is the motor. Omega over here, 1 over S, theta over here, this theta is being fed back. Now please note my point. What I want to say is that I have taken the transfer function between omega and the input to the motor. The input to the motor is control phase voltage. Now that will depend upon this device. I am going to tell you that there may be a device over here which is going to produce a low frequency signal. In that particular case, that EC is the input, and the transfer function which we have derived should be used the way we have already derived it. Now suppose I have a device over here, this device, which produces a carrier modulated signal, which is the signal which is being fed to the control phase of the motor. In that particular case, as far as motor is concerned, that motor is taking or getting a carrier modulated signal directly as an input signal. So it means, as far as the transfer function is concerned, it appears I should take the transfer function between omega and the carrier modulated signal. Okay? Here just I wanted to convey this point here. If this is the input signal coming from this particular device, in this particular signal the actual information about the control is carried in the envelope only, and this particular carrier signal is simply the operational frequency of the motor. What I want to convey to you is that this operational frequency may be 50 cycles per second, maybe 400, maybe 1000. It simply depends upon the design of the motor. It simply depends upon what the manufacturer has given to you. And as far as the system is concerned, as far as the control information is concerned, the control information is carried in this envelope, and therefore the mathematical model of the system could be taken as the relationship between the speed or the position as the output signal and the envelope of this particular signal as the input signal. So my point is this, that to the AC motor, if the signal is directly a low frequency signal and is coming to the AC motor through a modulator, in that particular case that low frequency signal will be taken as the input for the motor. But if to the AC motor a carrier modulated signal is coming as the input signal, in that particular case I will take only the envelope of the modulated signal as the input to the motor as far as control application is concerned, because this particular frequency is just an operational frequency of the motor and it simply depends upon the design of the motor. You may use a 50 cycles 50 hertz motor, the operational frequency will become 50 hertz. You may use a 1000 hertz motor, the operational frequency will be 1000 hertz, but the envelope will remain the same, because this envelope is an information carrying signal, and this information is the information about the discrepancy between the commanded position and the actual position. Is it all right, please? And this, even if it is not very clear at this stage, I assure you will become very clear when I take the control system applications, when you will see that there are devices which actually give you the carrier modulated signal directly to the motor, and you will extract the envelope of this particular motor as far as the input output relationship is concerned, because this carrier frequency is not important. Now if the carrier frequency, I made a statement which is a weak statement if not a wrong statement. I said carrier frequency is not important. It's not that, it's important, but the importance is taken care of in a different way. So when do I select a motor of 50 hertz or a motor of 1000 hertz? Please see, if this is the question, what is the selection criterion? You see that AC motors naturally are not going to be susceptible for low frequency noise. So if I assume, or if in an application I expect that there will be low frequency noise, I should take up a motor of high frequency. That is why in aircraft and missile systems normally 400 hertz or 1000 hertz motors are used, but for ground applications we use 50 hertz motor and not the high frequency motors. It depends upon the application. In aircraft systems the low frequency noise is presence abundantly, and to filter that noise, to reduce the effect of that noise, we normally go for high frequency motors. So whether the selection is 50 hertz or 1000 hertz, please see, it depends upon other considerations, and therefore in modeling I will not like to bring this aspect at all. So I will say that as far as the information is concerned, the information is carried in the envelope of this particular signal, and therefore the motor model which I have written as omega over E C, or E, let me say, or EC can be taken, Km over tau ms plus 1 is the model between omega, the speed, and EC, the information carrying signal to the motor. This is what I want to say. There may be a difference between the actual signal going to the motor and the information carrying signal to the motor, and my interest is about the control information, and the carrier is not important to me in modeling, and therefore I am extracting that information from the modeling, and my mathematical model is between omega and the information carrying signal to the motor. I hope this point is well taken, and I assure you that this will become more clear when I take the specific applications wherein you will see the information carrying signal to the motor could be a modulated signal. This is going to be clear later. Now before I come to an application, a full-fledged application of a position control system, I need one more device, and that device is an AC error detector. With these two devices I should be able to give you an application. With that application should make all these points also very clear. An error detector. Now again, your knowledge of AC machines will be utilized over here, particularly transformer. Just see, in this particular case I take a device whose schematic I am giving you. My diagram may not be good, you may not like it, but at least it should convey the message. This is a dumbbell rotor, a particular construction. On this particular rotor I show a winding, through the slip rings I give the supply. Okay. Now on the stator is a slotted stator, but schematically, if you don't mind, I could show it this way. This will make my derivation of the mathematical model more clear. So I am taking here 3 windings, call it S2, S1, S3, 1, 2 and 3. This is a stator. This is actually a connection this type in the winding. This is neutral, S2, S1, S3. Schematically I am showing it this way, it will help me. The winding arrangement in the stator is this way. Space distribution is 120 degrees. Neutral however is not available to me. S1, S2, S3 are the 3 terminals available to me. I want you to give me the mathematical model for this system, or how this system behaves. We want to see this point. Now see this, the linkages of the 2 fluxes. You see in this particular case, when you give this supply, the rotor produces a magnetic flux, and this flux links with the stator windings, and hence EMF is induced at the terminals 1, 2 and 3. So the output in this particular case is the EMFs available at S1, 2, 3, and the input in this particular case is the rotor position. Please see, I can change this particular position. So it is a device called a synchrotransmitter. The name of this device is synchrotransmitter. Okay. In this particular case, the input output arrangement you must see, the AC voltage to the rotor is a fixed voltage, it is the auxiliary supply. You are not changing this voltage. What you are changing is the rotor position, and in response to this particular rotor position, the three voltages at the three terminals S1, S2, S3 should change, and the information about the rotor position theta should be carried in these three voltages. Okay. Now help me, how will these three voltages be the linked to this particular theta, or the relationship to theta is to be determined. In this particular case you will find that if this rotor angle, the rotor angle over here theta, let me take with taking this as the reference, I rotate this taking this axis S2 axis as the reference, and with respect to this reference I take theta. If theta is equal to 0, the maximum flux is linked with S2, and therefore maximum voltage will appear over here. If I take this voltage to be ER sin omega CT, what is the voltage across S2 please? ES2N is equal to KER, look you can say some K constant, sin omega CT, for theta is equal to 0. Okay, maximum voltage is induced. Now tell me please, what will happen if theta is equal to 90 degrees? What will happen as far as the voltage at the S2 terminal is concerned with respect to neutral, for theta is equal to 90 degrees? It's going to be 0, and therefore I can say that at any position theta, the voltage is going to be ES2N is equal to K ER cos theta sin omega CT. This is going to be the voltage, okay, between S2 and N for any position theta. Similarly, with the same reason, I can write ES1N. This you can now verify very easily, KER cos theta minus 120 degrees sin omega CT, and the third voltage ES3N is equal to KER cos theta minus 240 degrees sin omega CT. These are the three voltages by transformer action. Now since the neutral terminal is not available to me, I will take only the terminal voltages, and this is a simple exercise left to you to determine that ES1 S2 is equal to, add up algebraically adding the two voltages, K under root 3 KER sin theta plus 240 degrees sin omega CT, ES2 S3 is equal to under root 3 KER sin theta plus 120 degrees sin omega CT, and lastly ES3 S1 equal to under root 3 KER sin theta sin omega CT. This can easily be examined, you see. Just for example, what is ES1 S2 equal to ES1N plus EN-S2 equal to EN equal to ES1N minus ES2N. Just add up the two voltages and you are going to get the three terminal voltages. I leave this as a simple exercise for you. Now help me just look at these three equations. What will happen if theta is equal to 0? Look at the terminal voltage. Suppose you have the measuring devices and you measure these voltages. What will happen when theta is equal to 0? You recall, when theta is equal to 0, maximum flux is linked with the S2 windings. Now look at the terminal voltages. What will happen to ES1, S1, S3? You find that ES1, S3 becomes equal to 0. Okay? So this particular position, I give you a definition over here. When the voltage across ES1, S3 is equal to 0, the corresponding position of the rotor is called its null position, and your theta is equal to 0 reference is given by this null position. This you are going to conduct as an experiment also in the lab. So if you have to determine the null position, that is the reference position of the rotor, you will measure S voltage across S1, S3. When this voltage becomes equal to 0, mark that position as theta is equal to 0, and all the measurements of theta should be done with respect to that position. Okay? So, in the null position, keep in mind, in the null position, maximum flux is linked with the S2 winding, and the voltage across S1, S3 is equal to 0. Yes, please.
So why are the directional theta always stand apart?
No, the directions of theta are not opposite. I am sorry. Then my diagram is, this diagram is only to show you that you have a shaft by which you are rotating. I am sorry, this should not confuse. Let me not put a theta over here in that particular case. This is only a mechanical arrangement to rotate your theta. That is, any device which rotates theta is given by the is shown schematically like this, and with respect to null position, this is the theta over here. Is it okay, please? Okay, I hope your confusion is taken care of. This is only to show the prime mover for this, you can say, as if. Fine. Now, tell me one simple question I'll ask you, which I have been asking the students in the labs when they conduct the experiment on this. Is this device a three-phase device? Look at the three voltages, ES1, S2, ES2, S3, ES3, S1. Is the device under consideration, the synchro transmitter, a three-phase device?
Single phase in time.
Single
Well,
phase
the device is a three-phase or single-phase only with respect to time. You have very rightly answered it. Since it is in time, they are in phase, so it is a single-phase device, surely. Because only the amplitudes are changing, you will see. All the three voltages are in phase. Only the amplitude of the three voltages is changing, and therefore the device under consideration, many times it confuses with respect to the equations. That is why I made a specific mention. Some of the students have been answering it as a three-phase device. It is a single-phase device, you have rightly answered it. Its magnitude is changing, but the phase, all the three voltages are in phase. Okay? This is a synchro transmitter which has the input as the rotation of the shaft theta, and the output are the three voltages, and these three voltages carry the information about the device or about the rotation theta. Now actually what my interest is in a control system application, I think I should be able to complete this diagram as far as discussion is concerned before I close today, so that next time I give you directly the control system. Let me say that this is the rotor, slip ring arrangement. Here I have three windings, S1, S2, S3. I have another rotor here. Well, again I said that hopefully I should be able to draw a sensible diagram at least. This is a rotor. The construction is different than this rotor. I am going to give you the reason, and let me say that I have three windings here as well. Okay? I have two machines now. You please note that these are the two machines. Here the rotor is a dumbbell construction. Here I have tried to make it more or less cylindrical. You see that the diagram may not be the way what I wanted to tell you, but in words I want to explain that. I just wanted to make it more or less cylindrical. The reason being that the output of this particular rotor is going to a signal conditioning device, an amplifier maybe, or a demodulator. Here is a signal conditioning device, and I really want that, this is a signal conditioning device, I really want that this particular device should see a constant impedance. If the rotor is not cylindrical, then the impedance as seen by the signal conditioning device will become a function of the rotor position. So I have made it more or less cylindrical, so that the impedance as seen by the signal conditioning device is not a function of the rotor position. This requirement is not that stringent in the earlier case, and therefore in the earlier case you can have a dumbbell construction. You can have a dumbbell construction. No one prevents you in taking the cylindrical construction there as well, but probably we save in cost, and that is why in the synchro transmitter, that is in this particular machine, we can go for a dumbbell construction. While the construction has to be more accurate here, the rotor has to be more cylindrical here, so that the impedance at these particular points as seen by the signal conditioning device is constant. Okay? So this, let me say over here, signal conditioning. The output of this is going to a motor, and this motor is going to control the position of this particular rotor. This motor is going to control through a gear train, of course, if necessary, it is going to control the position of this particular rotor. This is the construction, this is the arrangement, that is the two stator windings are joined this way, and here is the prime mover or the mechanism for moving this particular rotor, and let me call this rotor as this motion as theta r, and let me call this motion as theta c. This is the device I am going to use in my servo applications. Please see, in this particular case, this unit, the two are identical. You see, the two units are quite identical, but for the rotor construction. Okay? This particular unit is referred to as a synchro transmitter, and this unit is called a synchro control transformer. This may please be noted, a synchro transmitter here and a synchro control transformer here. And the objective in this particular case, the input output, you see, what is the input? The input in this particular case is the deviation of the two shafts, theta r and theta c, and the output in this particular case is the output voltage available across the rotor terminals of the control transformer here. Well, unfortunately, the constraint of time, I have not been able to complete it, but next time I am going to start with this diagram only. Thank you.